Perfect. Okay, once again, if you have questions, please, you can ask those in the chat directly. And at the end of each presentation, we are going to select a couple of them so that the presenter can answer them orally, and the other will be addressed through the chat. Okay, now it's 9:10, so I suggest that we start. And for that purpose, I am going to give the floor to Iris de Krom from VSL, who is the coordinator of the MetCCUS project.
Yes, thank you, Miguel. Good morning, everyone, and welcome to this seminar today. I'm really looking forward to it. Together with the project participants of the MetCCUS project, we set up a really interesting program, I think, with more than 10 speakers talking about different subjects, but all related to CCUS, or carbon capture, utilization and storage. And I'm not going to introduce them one by one, but I think it will go by itself. Miguel will introduce all of them once it's time. And before we start with all the different presentations, I would like to give an overview of the MetCCUS project to give you an idea of our goals and what we will be working on in the coming years. So if we can go to the next slide, and already the next one as well. Yes, thank you. So just to start very general, I think you are all aware of climate change and the ambition of the European Union to become carbon neutral by the year 2050. And to do so, they set up the European Green Deal, which is sort of a roadmap to make sure that we can achieve a carbon neutral economy by the year 2050. And one of the priority areas is clean energy, and solutions for this are the production and use of clean hydrogen, the use of fuel cells and alternative fuels, storage of energy, and carbon capture, utilization and storage, or CCUS. And CCUS is a technology to decrease CO2 emissions from fuel combustions and industries like refinery, cement and steel industries. And this is a key solution to decrease the CO2 emissions. CO2 is the primary greenhouse gas. And yeah, this CCUS technology is key to make sure that these processes and these industries can achieve zero emission of CO2. So in the next slide, what am I actually talking about when I'm saying CCUS, so carbon capture, utilization and storage? So industry emits CO2. The CO2 can be captured. This can be done by chemical absorption using amines, physical absorption, or for example, membrane separation, but there are many other possibilities to capture the CO2. Once the gaseous CO2 is captured, it will be compressed to a liquid or to a supercritical fluid. And then it can be transported via road or also through pipelines to its final destination. And this can be utilization. So that means that the CO2 is transformed into other products, such as carbon neutral fuels, minerals, chemicals, biofuels. But it can also be used in the food and beverage industry. And another option is storage of the CO2. This is usually done as a supercritical fluid in rock formations, underground or subsea. And this is a way to permanently remove the CO2 from the atmosphere. So this is a very versatile process, and it can be used by any industrial process, or it can be added to any industrial process to capture the CO2. But the CCUS process is an upcoming technology, and that means that there are many challenges to overcome, such as setting up a infrastructure for storage of the CO2, but also finding new utilization pathways to use the CO2 for development of new products. But next to that, also regulation to set up documentary standards, specifications. These things are still under development and still needs to be done. And next to that, what I think is very important is to set up a measurement infrastructure. And that is what the MetCCUS project is working on, to set up a metrological sound measurement infrastructure for the CCUS industry. And in the next slide, you can see that the project started on the 1st of October 2022. It will run for 3 years. And we have 21 participants in the project, which are different national metrology institutes, universities, research institutes, and also industrial companies. And the MetCCUS project is part of the European Partnership on Metrology, which is a program under Euramet. Euramet is the regional metrology organization in Europe, and their main task is to make sure that national metrology institutes work together in fields such as research, development of national measurement standards, traceability to the international standards, and also calibration and measurement capabilities. So why is metrology so important for the CCUS industry? So in my next slide, I will start with just a basic overview of metrology. So metrology is the science of measurement. And that is a way to make sure that you can obtain reliable, comparable, and trackable or traceable measurement results. And this all starts with the international standards. And this is built up of 7 base units, which are the kilogram, meter, second, ampere, Kelvin, mole, and candela. And national measurement institutes have the public task to maintain and develop national measurement standards, which are directly traceable to the international standards. And the national measurement standards developed by NMIs, or National Measurement Institutes, metrology institutes, are compared with each other in key comparisons to make sure that we obtain reliable and comparable measurement standards. And these can be used to develop reference materials or to calibrate equipment from calibration laboratories, industries, and testing laboratories. And in this way, everyday measurements can be directly traceable to the international standards through a chain of calibrations, like shown in the pyramid on the slide. And why is this also important for the CCUS industry? When looking at the carbon counting, it's very important to know your CO2 flow, CO2 emissions, and also your CO2 composition to make sure that the CCUS industry knows exactly how much CO2 is captured or sent into storage or for utilization. And also the composition of the CO2 and the physical properties of the CO2 are very important to ensure safe and efficient operation of the CCUS technology. And therefore, the MetCCUS, together with industry, identified 4 measurement challenges, which we are working on in the coming years. And those are shown on the next slide. Those 4 measurement challenges are flow metering, emission monitoring, chemical metrology, and physical properties. And during the presentations today, you will see that these challenges will come back in every presentation. Maybe some will discuss just one, others will discuss a few of them. And before we start, I would just want to say a few words on each of these challenges and what the MetCCUS project is going to do, or which kind of activities they're going to perform to work on these measurement challenges. So on the next slide, we start with flow metering. So there are many regulations and specifications which set requirements for the flow metering or the calibration of flow meters, such as the European trading system. But currently there are no primary facilities to calibrate flow meters with CO2. And therefore the MetCCUS project will develop primary facilities to calibrate flow meters with gaseous CO2 with an uncertainty smaller than 2.5%. And we will look into the requirements and needs to set up a primary facility for measurements of liquid flow with CO2. And once these measurements or these facilities are in place, the CCUS industry will be able to calibrate CO2 flow meters with CO2 and be able to comply with legislations such as the European Trading System to determine the flow of CO2 and also emissions of CO2, which brings me to the next measurement challenge on the next slide, which is emission monitoring. So the European Union acknowledged the use of CCUS as a good technology to remove CO2 from the atmosphere. But they have also concerns about the environmental integrity. So how can we make sure that when we capture and transport and store CO2, that the CO2, but also impurities in the CO2, don't escape into the atmosphere where they can harm the environment or also human beings? But currently, there are no methods to monitor emissions of CO2 or to calibrate and validate equipment to monitor the CO2 emissions. And therefore, the MetCCUS project will set up measurements to monitor CO2 emissions by setting up facilities which can simulate CO2 leaks. And then that way they can use this to validate and to calibrate leak monitoring equipment. They will also develop measurement methods to measure the emissions of degradation products from capture solvents. And they will do this for different CCUS infrastructures, so pipelines and storage locations. And once these facilities are in place, the CCUS industry can use leak monitoring equipment with great confidence and make sure that there are no leaks of CO2 into the atmosphere. The next measurement challenge on the next slide is chemical metrology. So when you capture CO2, it's never 100% pure CO2. It will contain impurities like permanent gases, but also compounds like water, hydrocarbons, and reactive components. But storage locations and also industry using CO2 for utilization, they have specifications on how much of these impurities can be present in the CO2. So to determine this, you need primary reference materials of these impurities in CO2 and at relevant amount fractions. And currently these don't exist for all the impurities. So therefore, the MetCCUS project will develop primary reference materials of impurities in CO2 at relevant amount fractions. We will also develop methods to analyze the impurities in CO2, online methods and offline methods. And of course, when you want to measure your CO2 stream, it's also important that you can take a representative sample of your CO2 stream, and therefore we will also look into material compatibility for the sampling of CO2. So when you use the reference materials that we developed and the analytical methods, then you can make sure that you obtain accurate measurements, reliable measurement results, and you can comply with the specifications for the composition of the CO2. This is important for utilization to make sure that no harmful impurities end up in final products. And it's also important for storage. So when you have, for example, water and reactive components such as sulfur compounds or nitrogen oxides in your CO2, they can react with each other. They form acids, and they can lead to corrosion of pipelines and storage locations. Also, permanent gases in the CO2 can change the compressibility of the CO2 and make sure that there is less storage capability for the CO2. And that this also changes the physical properties of CO2, which brings me to the last measurement challenge that we are working on. Because CO2 has very unique fluid properties. At room temperature and atmospheric pressure, it's a gas, but already at 57 bars, it becomes a liquid. And at 31 degrees and 74 bars, it becomes a supercritical fluid. And in many places of the world, 31 degrees is just a normal atmospheric temperature. So that means that it can be very difficult to control and to measure your process, because just small differences in temperature and pressure can lead to large differences in the fluid properties of CO2. But there are gaps between experimental data and the behavior of CO2 in combination with impurities often found in CCUS processes. So therefore, the MetCCUS project will set up experiments to obtain data on the properties of CO2 in combination with capture solvents. We will validate equations of state which are relevant for CCUS processes and for flow metering. And finally, we will also set up experiments to look at corrosion of CO2 pipelines and set up methods to calibrate humidity in CO2. And with these experiments and also with the data we obtain, we can make sure that we know more about the behavior of CO2 in combination with impurities. And this will help the CCUS industry to have a safe and efficient operation of the CCUS process. So that brings me to the final slide. So in conclusion, the MetCCUS project will develop standards and reference materials, calibration and measurement methods, and based on our results, we will write good practice guides, literature reviews, and peer-reviewed articles. And with our results, we can develop key documentary standards, but we can also provide input for specifications and regulations. And when you use metrological sound measurement methods and reference materials, you can obtain accurate measurement results, reliable measurement results, and also comply with specifications. And this will help the CCUS industry in Europe to grow, to have a safe and efficient operation, and in the end, to overcome climate change and become carbon neutral by the year 2050. So that was it from my side. Thank you for your attention. If you have any questions, you can write them in the chat. And I don't know if we have time to answer one of them now, otherwise I can give you a written reply in the chat as well. So I hope you're going to enjoy the presentations today. And by the end of the seminar, I will come back and say a few words about the measurement challenges that I came across today during all the presentations that will be given. So thank you for your attention and enjoy the rest of your day.
Thank you, Iris, for the good presentation. I see that we have one question in the chat concerning emissions. So basically, to clarify the terminology, vented emissions, and also what is meant by diffuse emissions. But we can also answer directly in the chat.
Yes. Miguel, do you want me to answer that? Or
please,
I'm writing a reply.
That would be great, Rod.
I can give a quick answer to Mires. We use the term diffuse emissions in the EN 17628 standard on VOC emissions to include the combination of the large, or a suite of vented emissions and process emissions that Mires mentioned, together with the fugitive emissions, which are the leaks from contained systems. So diffuse is the sort of set of all the emissions from a site that are distributed across the site, rather than just fugitive, which are the leaks or the process emissions. So it's a kind of term that covers all of the individual leaks across a site.
Yes, thank you, Rod. It's really helpful.
Thanks, Rod. I think it's good to keep the distinction rather than having this not so precise term. So I leave it up to you, but my recommendation would be to, there has been a lot of discussion already on the methane emission side to be explicit about the meaning of fugitive and vented emissions, that I think it's useful to capitalize on that. But just a suggestion, up to you.
Yeah, and I'm very keen that we get the terminology defined. So yeah, I agree with you.
Thank you. Thank you for the reply.
Thanks, Rod,
and for the question, Mures. I suggest that we can continue dealing with the questions in the chat, since we need to continue with the agenda. And now I am happy to introduce our next speaker, Ana Rita Baldan from VSL, who will give us an overview of the EMN energy gases. Thank you for joining, Ana Rita.
Thank you, Miguel, and thank you for inviting me to this seminar. My name indeed is Ana Rita Baldan, and I'm the chair of the European Metrology Network for Energy Gases. And I use this short slot to introduce you to the network, and then I leave you to the more technical details of the CCUS measurements and disciplines. Next slide, please. It is already introduced the background of the research and work in CCUS, why it's needed. So I'm not going to explain this again. It's important to say that in the future, or we already see it, there is a complex mix of energies coming up. So it's important to make sure that they can live also together, and therefore measurements are also important. Creating the proper measurement infrastructures is very important. Next slide, please. So why the European Metrology Network for Energy Gases has been created? There is, in a large sense, a need to comply with the quality, the efficiency, and safety in production of energy gases, in transportation along the whole supply chain until the use, and to ensure a fair exchange of energies between countries for trade, but also for consumer protections when it comes to billing. And to do that, the big challenge is to make sure that the measurement infrastructure is in place to have reliable and robust measurements. And this is going beyond the national boundaries and beyond the single technologies. For this reason, there started a European coordinated effort in order to ensure that the metrology institutes in Europe work together to engage with stakeholders to understand the needs and to make sure that these needs are addressed in the most efficient way. Next slide, please. So the Network for Energy Gases was started in 2019. We operate under Euramet, and Euramet is the European Associations of Metrology Institutes, Measurement Institutes in Europe. We are at the moment 19 members, and shortly we will become 20, and we cover, let's say, all. We are spread around Europe. You can see the yellow dots on the European map, which is very nice because we cover the different needs from north to south, west to east of Europe. Apart from myself, we have a vice chair, which is Carina Reinius from RISE in Sweden, a secretary, Marcel Workham from VSL, the Netherlands, and a steering committee composed of different experts from different metrology and designated institutes. And we work, in short, in task groups in order to focus our work, and so that the different our plans are and activities are covered. So we have a strategic research agenda which covers what metrology institutes have to do to address all the measurement needs coming from stakeholders. We have a task group on measurement service platform, which aims at explaining what are at updating what are our services in terms of metrology, so calibrations, for instance, and make sure that they are visible. We have a task group on stakeholder engagement, and we work also very close with standardization, because metrology and standardizations are necessary and interacting with each other. And we have then other, you can go further, other 3 task groups, but they are more internally oriented. So what do we do, in fact? We focus on metering and use of energy gases, and we cover the, you can see it on the right side, on the right low side. We cover different energy gases, from natural gas to the liquefied natural gas and gas, biomethane, hydrogen-enriched natural gas, hydrogen, and we also cover carbon capture and utilization, because it's part actually of the energy field. So our mission is to be a world-leading network, metrology networks, which supports with this expertise, innovation and acceleration of decarbonization and reduction of emissions, specifically in Europe. But of course, by doing that, we collaborate also with other networks and research groups and metrology institutes outside Europe, other regions, and to make sure that our work is harmonized. So we engage with different stakeholders, from industry, regulation, and standardization. We have very good contacts with the hydrogen associations, Hydrogen Europe, with partnerships with GERG, the organizer of the meeting today, Microgas, DG Energy, and so on. We act as the European Metrology Center, facilitate the energy transition by coordinating measurement research based on stakeholder needs, and we try to boost access to metrological services and calibration facilities. And as you see, we have a cross-cutting character, so we cover different disciplines, and that's the main core of the strength of this network, because the experts come from different disciplines, from gas composition, flow, temperature, pressure measurements, humidity, particles, material data, material testing, and calorimetry. Next slide, please. So we have a strategic agenda, research agenda, which is available on our website, and focusing on 4 pillars: decarbonizing natural gas, decarbonizing industry, energy transport and storage, and cleaner fuel for mobility, with the objectives of facilitating, again, research projects for development and innovation in collaboration with industry and other research parties. And I would like to remind you that if you don't know, that the next we have the Euromet is coordinating a European metrology research program called the European Partnership on Metrology, where a research program is planned, and the next year call will be on Green Deal. So any need coming out from this workshop will be fed into research proposals in the next call. And as you see, there is a broad set of portfolio of energy gases, which are now projects which have been running from 2010, when the first program started, and continuing up to now. And the MetCCUS is one of the project under this portfolio. Thank you. Next slide. As I mentioned, we have a measurement surface platform, and this is visible on our website. Again, it's to explain, to give an overview of what our services, which are, of course, relevant, because once we have done research, address research, this research is becoming a service for the for the outside world. So if you're interested in our capabilities, please look at this website. Next slide, please. So in conclusion, the drivers to act to address climate change and energy transitions are clear. The European Metrology Network for energy gases is established with a focus on sustainable energy gases and decarbonization. Metrology and the related research projects aim at developing a measurement infrastructure which support the transition and the emission reductions by developing measurement methods and standards. Of course, we look forward to engage with all parties involved in the energy gases field, and in particular, we would like to engage even more with the CCUS stakeholders. So if you have interest, please, next slide. If you're interested in our network and you want to establish us, please contact me or us at the email address, which is on this slide. That's all from me, and thank you very much.
Thank you very much, Anna Rita, for accepting the invitation and for telling us a little bit about the EMN energy gases, which of course is a very important program for the MetCCUS project that we are presenting today. So thanks again. And I also want to take the opportunity to thank all the different stakeholders, because you know that we have an advisory board in MetCCUS, and many stakeholders accepted the invitation to be part of this public seminar. So thank you very much for being engaged, as well as, of course, as the different partners in the consortium of MetCCUS, since we have today speakers from both the consortium and also stakeholders, external stakeholders from the advisory board. And that leads me to one of these engaged stakeholders that we have, which is CO2 Value Europe. I'm pleased to introduce Anastasios Perimenis, who will give us an overview of CCU in Europe. Welcome.
Thank you, Miguel. Good morning to everyone. I am indeed a proud member of the external advisory board of MetCCUS. Also on my side, a more macro level presentation, especially for one of the finalities of carbon capture, in that sense, the utilization. Whenever relevant, I will also give some information that might be relevant also for storage. But before you go to the hardcore technical presentations, I would like to make a link on why metrology is important, and that all the downstream things that will be happening at utilization or at storage level will not be able to be fulfilled and covered if we are not able to measure properly the CO2. So this is the link that I will try to establish at a more macro level and focusing more on CCU this time. For those who don't know us, CO2 Value Europe is the European association that is representing the carbon capture and utilization community. And we bring stakeholders from the complete value chain, so from the CO2 production to the CO2 conversion to the utilization of the final product. And it's a cross-sectoral issue, and it's across industries. And that is why we consider ourselves to be quite representative of the entire value chain. In the next slide, you will see a slide with some logos, not to impress you, but basically to show the attribution of our members and the even distribution of them, from large companies that are searching for solutions for their emissions to SMEs that are technology providers and provide the technology that provide the solution to do something with the CO2. We have research organizations, and we have also industrial clusters, regional clusters. So it's a quite even distribution along the entire chain. And we think that this is a very good sign because it's a cross-sectoral issue, as I explained. In the next slide, I will, and in the ones following, I will focus on our priorities so that you can understand also what we're doing, and then I will go into more detail later on. So we have 4 basic priorities. The first one is to gather and mutualize knowledge about the development of CCU, scientific, technical knowledge. What are the technologies? Who are the actors behind them? What level of maturity they are? Information on life cycle assessments, techno-economic assessments. So try to be as evidence-based as possible on the information that we provide on CCU. Second activity is to work on the regulatory framework and the policy framework. You will see later on that it's a very complex framework, and make sure that it is consistent for the future deployment of CCU at scales that are industrially relevant. Third thing of what we're doing is to try to bring actors together to develop projects at lower TRL, at higher TRL, and also help them get funding for such projects, depending on the funding source. Could be private, it could be public. We are, for example, participating in the expert group of the Commission in the Innovation Fund, so we follow these activities, and you will see also some examples later. And the fourth thing is what is included behind the term communication. So not only about our association, but about the subject, about CCU. Not everybody knows what CCU is, and there are also misconceptions, confusions. CCU, CCS, CCUS, CDR, and all these elements are important, and we need to communicate properly. We need to raise awareness. We need to engage with other stakeholders so that we understand the merits and limitations of each of those technologies, but all of them will be needed, undoubtedly. Following up on the listing of those activities, if you want to know more about CCU development at current times, you can follow the database that we have created. It's publicly available. It's also directly accessible from this link, but also from our website. And there we have, for the moment, 3 sections. A section that gathers all CCU projects that have been announced, that are there ongoing or announced in the upcoming years, and we will see a lot of them that are expected to be operational within the next 4 to 5 years, and at industrial levels that will produce around 50 to 100,000 tons of final product, be it on the chemical side, on the fuel side, or on the mineralization, so materials side. We have expanded it recently to present also companies, so CCU technology providers that are active in the scene. We have expanded it also to some news from EU-funded projects, like milestone news, not to replace the news sections of each individual EU project, but try to maximize the impact by using our network and bring more visibility to these EU-funded projects. And just some metrics for your information. For over the last 3 months, we had around 1,700 new users and around 2 minutes and 20 seconds of average engagement time, which I hope you won't ask me what it entails, because I'm not exactly sure what is behind the engagement time, but I think it's something that how much time people stay on the site and click around. The next slide is about funding. So I'm giving a broad overview of CCU deployment. We have one of the largest innovation funding schemes in the world, probably. It's called the Innovation Fund. Most of you have probably heard about this. We're members of the expert group of the Commission on the Innovation Fund. And just to give you an example of the development of the CCU and CCS scene, is that recently we had the results of the third large-scale call, as we call them, and we had 41 projects that have been selected for funding. with an overall budget of all of them to be around 3.6 billion to be granted to those projects. And interestingly, more than 25%, at least 12 projects, have an element of CCU or CCS in them. They're scattered around Europe, which shows that among the eligible funding areas of the Innovation Fund, which includes also renewable energy production, renewable energy storage. So it is important to see how the funding of the CCU and CCS area is channeled through such public funding instruments. And the next ones, these are annual calls, and the next one will fund projects of small, medium, and large scale. It will open in November. It will close in April with around 4 billion euros to be granted. And there is also a new instrument. The Innovation Fund is evolving itself that will provide an auction on renewable hydrogen. So a competitive bidding system that will open at the same time and close a little bit earlier and will provide 800 million. And that's a pilot auction for the moment for renewable hydrogen only, but expected to be expanded also to further elements of the Innovation Fund. So Innovation Fund is one of the major high TRL, I would say, public funding instruments. We have also the Horizon Europe. In the first 2 years of its operation, more than 235 million euros have been granted to R&D and I projects of CCU proximity so far, and we are expecting more of them to be channeled also through the 2023 and 2024 work program, but also later on by 2027. So funding of these projects is important so that they show their potential, and by 2030 at least we see commercial-like facilities to be operating. So part of funding is one part. If we move over to the policy part, there is, I think it's the next slide, if you may. I call this the headache slide because it shows precisely how complex the regulatory framework is, and it's not that there is one CCU directive contrary to a CCS directive, but still also those directives would not capture the entire scope of how CCU and CCS is treated in policy. You see instruments that are bits and pieces of the CCU context is in different instruments. So you have instruments that are more on the upstream and how you regulate, for example, the access to renewable electricity, how you make sure that your CO2, for example, the ETS revision will not be double counted, but the entirety of the CO2 that will be released into the atmosphere will be accounted for. But if it's used, then it's not double counted again. You have more downstream instruments that regulate the share of products in a given sector, for example, Refuel EU in aviation or Fuel EU in the maritime. You have new instruments that have been proposed, like the Net Zero Industry Act, which has been a milestone also for the CCS community because of the obligation for an injection capacity of 50 megatons by 2030, and which is under discussion of what will be strategic technologies and what they would include. And the point being that what we need to make sure is that this framework, we have lived through a very dense policy-making period. Most of those instruments are part of the Fit for 55, which is part of the EU Green Deal, as Iris mentioned at the beginning. And we are now passing into a transition phase where most of those legislative documents have been finalized, most of them, not all of them. And now we're going into the implementation phase, which is equally important. So it was a very dense policy-making period, and there are still instruments, one of which I will also explain a little bit later, which is a quite crucial one for our for the CCU and the CCS sphere, which is the industrial carbon management strategy. But I will explain this a little bit later. Point being that these instruments need to be consistent with each other. So if you have, for example, quotas on how much your CO2-based synthetic fuels need to take up of the market, then you will need accordingly the flexibility of using CO2 from different origins and access renewable electricity, for example, under non-restrictive conditions. The next slide shows with some more concrete numbers, some of them, the ones that are most relevant for CCU and CCS, basically, for some of them. I will not go into each and every one of them. You will have the slides later on so that you can have this tracking. Normally, if I've done my work correctly, there are links behind each one of them so that you can check them. But the impact on CCU, as it appears, is the bottom line of everyone. Some are upstream, some are downstream. Important is to understand that each and every one of them, if we want them to be achieved, and if we want those targets to be covered, and this is sometimes the link that we miss, is that we need on the upstream to be able to measure our CO2 correctly, so that we know the CO2 that has been emitted is being incorporated into a product, and be able to measure that the CO2 will stay permanently in this product because it's mineralization and it's a brick and you can use it for construction, or it will be released again. It will substitute a fossil based product. CO2 will be released again, probably recaptured. So all this chain that is regulated from those policy instruments will need to show that we can reliably and accurately measure our CO2. And this is why this is how the link between the downstream and the upstream is being done. Examples: the certification for carbon removals, which is the last one that you see in the list. We will need to be able to show in the methodology of the certification of carbon removals that the CO2 is permanently bound, either in CCS application or in CCU application that is focusing on mineralization, for example. So we will need to be able to use accurate methods so that we can make sure that all of those instruments can be properly monitored, followed, and fulfilled. So that's more on the policy framework. The next slide shows two I would like to focus on two basic initiatives that are of interest also for this group. The CCUS Forum and the Industrial Carbon Management Strategy. So the CCUS Forum has been the platform, has been there since 2021, and it's the platform that will provide inputs for the elaboration of the Commission of the Industrial Carbon Management Strategy. We will include the CCS subject, the CCU subject, the carbon dioxide removals, the CO2 transport infrastructure, and it is expected to be released next year, beginning of next year. It has created working groups on industrial partnerships, on the infrastructure, on the public perception, on elaborating the strategy. And if you focus mostly on infrastructure, which is I assume of interest for this, for the project, also for MetCCUS, there have been issue papers released from the infrastructure working group on how to create a cross-border CO2 transport and storage infrastructure, or how to come up with an interoperable CO2 transport network with specification for the transport of impure CO2. A new study has been released in March on the EU regulation for the development of a market for CO2 transport and storage, and there's a new study, upcoming study on from JRC on the scenarios of infrastructure development for cross-border CO2 transport. So these are expected to come in the next, I think, weeks, if I'm not mistaken. The CCUS forum will have its plenary in November. Please register and follow this as much as you can. And it will be the body, so to say, the forum where we will see how the development of the strategy is advancing. That will be published during the first quarter of 2024. So we are participating in the CCUS forum, as many of other stakeholders that are also in the lineup also today. The second part that I would like to focus on, which is a rather new activity also for us as CO2 Value Europe, is, and it appears on the next slide, it's about the 10-year network development plan, which is an exercise happening every 2 years from the transmission system operators for electricity and gas, so for ENTSO-E and ENTSO-G, to develop scenarios for how the future energy system will be will seem. Starting from national investment plans of national TSOs, but also from stakeholder feedback on some input parameters and methodologies for the scenario building, the TYNDP provides modeling scenarios of future infrastructure development. So some of those scenarios, as you can see the image, which is now, I realize it's quite small, but it's the national trends scenarios, and then how they deviate along the years with, let's say, incorporating the uncertainty of the infrastructure development. So CO2 Value Europe is part of what is called the ETAG, the External Technical Advisory Group, because CCU and CCS stakeholders have been expressly requested with a call for expression of interest, so that we can see how it's not clear yet, because it's a process that has started. There was an exercise in 2022. To the best of our knowledge, CO2 transport was not included, but now that the CCU and CCS activity is picking up again, we will have to see how to incorporate the infrastructure and the transport network of CO2 in the infrastructure development plan of the transmission system operators. There is a webinar on the future system needs on the 6th of November. I invite you to participate in this webinar to understand better what the TYNDP entails. And for most of you, being an infrastructure activity, I think it will be of interest also for the project to try to make those connections between infrastructure deployment and development and measuring needs for the particular for this infrastructure precisely. I believe that was my last slide. No, my last slide is the following. Also on our side, what we have realized is that looking up to 2050, we have undertaken the exercise to see what the contribution of CCU could be in a net zero world, realistically and feasibly. So we have undertaken an exercise with scenario building and modeling of CCU pathways, so that we can precisely answer to quantified questions like, how much will the CCU contribute towards the net zero goal? How much carbon we will need to capture, and where will it come from? And how much of it will be utilized, or how much of it will be stored? How much electricity we will need in order to cover the energy needs for some CCU pathways that are energy intensive? We have used the model of Klimact for that, and this report will be available as of mid-November, also feeding the industrial carbon management strategy, but giving a more quantified idea of what the contribution of CCU could be in our pathway towards net zero. And I think that was my last slide. If you have any questions, either now or later on, or overall, please reach out, and happy to engage with you. Thank you.
Thank you very much, Anastasius, for the interesting presentation. It's good to learn about CO2 Value Europe and also the overview that you gave for CCU to see that there are some funding opportunities here in Europe, as you mentioned, the Innovation Fund, but also Horizon Europe, which varies the level of TRL somehow. Also, this interesting database that you explained, I think it's really useful to see in real time, more or less, even if we know that this is evolving all the time, that there is progress, that there are projects ongoing, coming. So that's really good to know. To remind everyone, if you have questions, please feel free to put them in the chat. That way it's easier for us to deal with them, and we can address them right now or later on in the chat if there are no questions right now. For the moment, I don't see that there is any specific question addressed to you, Anastasius. So thank you again for the presentation.
Thank you for having us.
And that leads me to the next presentation in the agenda, which is presented by Philip Nel, who is going to talk to us about the requirements for CO2 flow measurement accuracy. Thank you very much for accepting the invitation and welcome.
Thank you, Miguel. So, yeah, thank you for inviting me to present in this meeting. My name is Philip Nele. I'm with TNO in the Netherlands. I don't actually have slides to introduce our organization, but I assume that that is not necessary. So I have a background in geophysics, and I've been active in CO2 transport and storage for the past 15 years or so. And my current role in TNO is to coordinate the work on transport and storage. I also have a role in the zero emissions platform, where I co-chair the network technology, which does studies and puts out reports along the lines that Anastasios just presented. So in my presentation, next slide, please. I will talk about not necessarily requirements for CO2 stream measurements from a technical point of view, but what I would like to do in the next 10 slides or so is to sketch the development of CCS that we see developing in Europe at this moment. So this is a very simple overview of my presentation. I have a couple of slides to give an impression of the CCS developments in Europe. It's clearly switching to a higher gear, many new projects in the pipeline, but still we have no commercial CCS projects in operation yet. And I'm assuming for simplicity that the two ongoing projects in Norway are not commercial projects, at least not in the sense that there are multiple suppliers to store the CO2. Then I will put my focus on the Netherlands for a little while to talk about the projects that are in development here, to also give you an idea on a smaller scale about the complexity of the infrastructure that is aimed for right from the beginning. Along the lines, I will be talking about transport modalities that include, of course, pipeline and ship that are being talked about widely, but I think that more modalities are to follow quite soon. On this slide, on the right-hand side, is just an illustration of CO2 transport that I came across on the internet. This is an example, apparently, of a CO2 truck delivering CO2 somewhere in the Netherlands, and you see people standing by, well, quite unconcerned, I would say, about all the CO2 that's apparently leaking from the process of delivering CO2. Lower in the illustration is one that I found at a Northern Lights site, which is an illustration of a modern variant of CO2 transport that will become reality in just a couple of years' time. So these are exciting times, I would say. Next slide, please. So first of a couple of slides talking about the projects that are in existence today in Europe. So this is a map that the Zero Emissions Platform put together. More than 60 projects of different type, also of different maturity, that are scattered throughout Europe. There is a certain concentration of projects around the North Sea. But the good news is that we have a lot of projects in the first place, and that projects are appearing in also other parts of Europe. Several of these projects are expected to come online, to become operational by 2030. There is a couple of storage projects in the map, green and orange, and these will be the first projects to link onshore emissions, onshore emitters to mostly offshore storage capacity. Next slide, please. This is a similar map, this one done by the IOGP, and I'm showing this one to highlight the fact that with all these projects near the coast, as well as projects in locations far from the coast, we see that transport modalities, in addition to pipeline and ship, are also becoming part of proposed projects. Of course, projects in the center of Europe either have to go and find storage capacity nearby, onshore that is, or they have to think about ways to get the CO2 to a coast and to have it stored in an offshore location, either the North Sea or the Mediterranean. So we see train and truck appearing in project proposals increasingly. Next slide, please. So this focuses on the storage projects. So same map as previous maps, but now only the storage projects. Several of those are close to investment decision, as I mentioned, to become operational by 2030. If we look at these projects and also innovation fund projects, transport that is part of them is expected to happen in many ways. We see gas phase pipelines, dense phase pipelines. We even see pipelines that are planned to switch from gas to dense phase. And we see ships popping up, and it looks as if ship transport is going to happen at medium pressure at first, but there are also many plans around for ships to be constructed to transport CO2 at low pressure. So to me, this tells us that there is going to be a wide variety of the phase of CO2 and the conditions under which CO2 is going to be transported. And it's likely that CO2 is going to be converted, if that's the right word, from one type of transport condition to other types of transport conditions, which probably has a bearing on the need for what sort of metering is needed, what sort of flow measurement is going to be required. Just one thing I would like to highlight is that at the bottom of the slide, it says that the 17 storage projects together plan to have a capacity of 35 megatons per year by 2030. And this already comes quite close to the requirement mentioned in the Net Zero Industry Act, as mentioned by Anastasios, of 50 megatons per year by 2030. So it looks like if plans are realized, that such a goal of 50 megatons per year by 2030 is actually feasible. Next slide, please. This is a map that shows the projects of common interest, or the projects of mutual interest. And these are, at least they used to be, transport-focused projects. And in the latest list of PCI, PMI candidates, storage was included as well. And then I'm showing this map because this map is showing the first elements of what could become a pan-European transport infrastructure. So we see blue lines, light blue and dark blue lines on this map, which represent planned shipping routes or pipeline corridors, again, that connect emitters onshore to storage capacity offshore. The current list of PCI candidates counts 18 projects. And again, it's good to see that we not only see projects around the North Sea, including Iceland, but we also see projects developing in or around near the Mediterranean. And again, this picture highlights the different transport modalities. So we see pipeline, ship, both onshore and offshore, barges, onshore barges and offshore ships, and even, I think, trucks are being considered. Next slide, please. So focusing in a bit on the Netherlands, we have several projects in development, all of which plan to be operational by or well before 2030. Going from top to bottom through the bullets on the left, the Portos project, which is the illustration in the upper right-hand side corner. This one is expected to be operational by 2026, the earliest of the three shown here. This is about bringing CO2 from 4 emitters in the Rotterdam port area to a nearby offshore cluster of gas fields, the P18 gas fields. The map shows an onshore collection network in purple color, which leads to a compressor near the coastline, which feeds into an offshore pipeline that again links to the 20-kilometer distant offshore platform. This is an interesting project because this one uses depleted fields, which pose very interesting challenges because of the low pressure in the deep subsurface. And the engineering solution that's adopted by this project is to have the offshore pipeline operate in gas phase at first and liquid phase later on when the depleted fields are at pressure. And the idea during the first phase, during the first gas phase storage, is to bring CO2 warm to the platform in order to reach the required injection rates. The pipeline will be insulated so that the heat, the compression heat, can be brought to the platform. So after a year or two, pressures in the subsurface are high enough, and the entire system is switched to higher pressures, and the CO2 is going to be then going to be transported and injected in dense phase. So that's the first project in the Netherlands by 2026, and it's already quite complex. Even though the layout is, well, not too complex, with a couple of emitters linked to a single pipeline that is in turn linked to 3 or 4 injector wells. Then the next one I would like to highlight is the Aramis project, illustration in the middle, which is about basically about constructing a trunk line from, again, the Rotterdam port area to the KNL blocks. This is an offshore region with a lot of depleted fields, or to be depleted fields, and a lot of storage capacity. This trunk line is to be oversized quite a bit compared to the initial volumes to be transported. It is to have a capacity of more than 20 megatons. And the initial storage projects linked to this pipeline will be those of Shell and Total Energies, who will start operation at 2.5 megatons per year each. The complexity in this case lies in the fact that this project now has 2 storage sites with, I'm not sure, at least 4 or 5 injector wells, a huge trunk line, 22 megatons per year capacity, and injection in dense phase, transport and injection in dense phase. The challenge in this case will be to ensure a constant flow rate to all of the injection wells, which each of them will have quite a narrow operational window. And this is due to the low pressure in the depleted fields at depth, and the high pressure in the dense phase pipeline. Flow rate is to be, well, fairly constant, and the idea is to regulate any supply variations from different suppliers onshore using a ship terminal that's indicated in the map in the middle, with the 3 next to it. This will be a 40 kiloton shipping terminal, allowing import by ship from Belgium, France, and this terminal will be used to even out any supply variations in order to have an as stable as possible flow to each of the wells. So in my view, again, this is going to be quite a complex project, And yeah, so as it says in the title, simple first, complex later, this is actually not the case. So this is going to be, yeah, very interesting to follow these projects, to see how they will operate, and to see the building up of experience with complex CCS projects. So I've mentioned the shipping terminal called the CO2 Next hub, which is going to be constructed right next to the compressor location close to the shoreline. Then the third project I would like to highlight is that of Neptune Energy, very similar to the Shell and Total Energies projects. It will be linked also to the Aramis trunk line. And there, and as far as injection challenges, this project is the same as those of Shell and Total. An additional complexity in the case of the Neptune project is that they are considering also direct ship transport to their offshore platform. So Neptune is looking at CO2 supply from the Aramis trunk line, as well as from ships that connect close to the platform to the injector wells. So that's an additional complexity there. There will be intermittency, of course, due to or as part of the ship supply. And that will have to be managed, again, in the light of the narrow injection operational window of the depleted fields and the depleted wells. All of these projects are aiming at becoming online by 2030 or before 2030. Also on this slide is mentioned Wintershall Dea, CMS, Carbon Management Solutions. They are developing their own fields, but their timeline is less clear. Maybe they make it in time to meet the 2030 deadline, if you like, but this is not clear. Next slide, please. So again, looking at the Netherlands, this is a map on the right-hand side of current gas lines and current gas fields. The fields are the not so well visible reddish blobs on the map, and the lines connect these blobs, the fields, to, of course, onshore networks and onshore consumers. A recent study shows that about 100 fields are out there that are likely to be suitable for CO2 storage. Together, they have a capacity of 1.7 gigatons, and a lot of the fields will be available, will end production in the next 5 to 10 years. If we look at industry in the Netherlands and the likelihood of their supplying CO2 to a CCS network infrastructure, then we can easily expect dozens of megatons per year supply for storage. Our neighboring countries, Belgium and Germany, and France too, have little or no domestic storage capacity, or storage onshore is prohibited in these countries. So they will be looking also at Dutch offshore storage capacity. And again, we're talking about dozens of megatons per annum that could come from these countries to Dutch storage, transport and storage infrastructure. If all that happens, then our fields will be full or starting to become in use quite quickly, and by 2060, with these volumes, our offshore area will be used to capacity, and we'll have to think about connections with our neighboring countries, the UK, Denmark, Norway, to connect to those networks, which will have a larger storage capacity. So what we see here is, in my view, a future CCS infrastructure that will have the qualities that you see in the map on the right-hand side here. Many branches, trunk lines, and I would think there is a need for flow measurements, composition measurements at all of the nodes in such a network. Next slide, please. This is just a small study we did recently for our own offshore, and it's included here just to give you an impression of the complexity of infrastructure, already only looking at the Netherlands. So we've looked at gas fields, depleted fields in our offshore that are likely candidates for CO2 storage. We've looked at realistic supply scenarios of CO2 along the lines that I sketched in the previous slide. What we see is in the illustrations on the right-hand side, hypothetical but realistic supply scenarios. These are the solid blue curves. And then we try to stack depleted fields in order to meet this demand curve. And we looked at different scenarios, and you see that we need more than a handful or even more than 10 or a dozen fields in order to meet realistic supply scenarios. So that's another way of getting a grip on the level of complexity, the number of depleted fields that will be needed, the number of injection wells, which will go up to 20 easily in the lower scenario. And for each of those wells, the operator will need to know how much CO2 goes into each well. Next slide, please. So this slide talks a little bit about this, wrapping up all the previous insights. So I think in the future, and this is not the not too distant future, we will see CCS, CO2 transport and storage using pipelines and ships. This is easy. We see lots of projects talking about those too. But we will also see an increasing number of buffers, ship terminals. We will see train transport. We will see projects utilizing trucks to bring the CO2 from their plant to a nearby shore hub that connects to a shipping corridor. We will see CO2 being transported and stored under various conditions. Gas phase for the collection networks, probably liquid phase when we talk about buffers and ships, and dense phase when it's about high pressure pipelines. The CO2 composition, I think this will be one of the key items for discussion and study in the coming years, in the immediate future. We start to see CO2 compositions, specifications appear. They're not the same, they're very different. this is causing concern with CO2 suppliers. CO2 composition that we see around the specifications call for CO2 to have a purity between 95 and, well, 100% or 99, let's say, purity. And we see lists of impurities with varying limits. And perhaps there is a need for a common composition, a common specification that allows emitters to link to various storage projects. And I'm thinking of a hypothetical CO2 supplier, well, at some location far from a coast, who will connect to a coast through barges, trains, and potentially onshore collection networks. And the CO2 from this emitter might end up in any of the stores that I talked about previously. And for that to be possible, for this CO2 to be transported through any of the transport sections and to end up in any of the connected stores, it will need to comply with all of the specifications that it meets, if you like, along its way. And I think that's going to be quite a challenge. On the right-hand side, just, oh, can I go back, please? Yeah, thanks. On the right-hand side, just a quick list of requirements that I could think of. So the CCS directive is asking for flow measurements into each well. I think storage operators will like to have a clear view of the flow to their storage site because they are dealing with contracts with emitters. A shipping terminal obviously needs to find out what flows in and out of the buffer. And at each hub or node in a network, there will probably is a need to find out what is going into each branch. Next and last slide.
Sorry, Philip, you were muted. Can you please unmute yourself? We cannot hear you.
I'm sorry, I must have touched my my computer. Sorry, so to wrap up, we see a steep increase in number of CCS projects, in interest in CCS. We see many transport modalities popping up, and we see a good discussion of CO2 specifications. Just a final remark, and I'm not sure whether this is of relevance to your project and to flow metering in general, but the flow rates that we see developing are really big. Megatons per annum easily, tens of megatons per annum, potentially in the medium term. And I'll stop there. Thank you very much.
Thank you very much, Philip, for your presentation. It was really interesting, your presentation about the CCS developments in Europe, but particularly in the Netherlands. As you all know, the Netherlands has an interesting history. If we talk specifically about the gas sector, and this is certainly a potential to be exploited. So because there is an infrastructure, there are some depleted gas fields that can be used for storage in the future. Of course, this means that there are challenges. You mentioned some metering challenges, CO2 composition. There will be a need for all these measurements that MetCCUS is addressing. And we see already some ongoing projects like Portos and Aramis. So the Netherlands is really adapting to what is required in order to change what its history, its past of the gas industry, and now move towards a more decarbonized, let's say, infrastructure also with renewable gases. Are there any questions? I don't see any question in the chat for you. I think we have time for one question before the coffee break. Alexander, I think you prefer to speak out.
Yeah, yes, thank you. I have a question actually for very last slide you have shown on the screen. Yes, thank you. The question is that what I can see, you ask, personally, of course, but in general, for this kind of project, you ask about transport, trucks, ships. You need purification 95 plus. And we know that transport is expensive. Pipelines in good quality are expensive. Cleaning of the gas is expensive. Do you have any kind of financial aspects about feasibility of financial feasibility, despite of political, of course, price, about this kind of projects? Because I'm wondering if there is any kind of business case in this kind of applications, because it's, for me, it's too expensive. And because if you're using also trucks, ships, or whatever, then they will also emit CO2. Then for pipelines, you need good quality steel. Then also it will emit CO2 once you produce something. So actually, where is the economy in this kind of approach? Thank you.
Yes, thank you for this question. Yes, this will be expensive. First, a reality check. We have the Portos project, if we stick to the Netherlands, which has taken investment decision just last week. They will go ahead. They will be in operation by 2026 as planned, which shows that in this particular case, in spite of the complexity of the project that I explained, that the capture, transport, and storage of CO2 is feasible. So there is a solution there that is apparently financially feasible. But you're right to be concerned about the cost of CCS, the cost of CO2 transport and storage for emitters that have higher cost of capturing, emitters that are at a larger distance from the coast, which may have to use several modes of transport in order to arrive at a well. I've seen figures for transport exceeding 100 euros per ton for emitters. I think this was central Germany. And then it's more difficult to get a closure on a business case. Of course, our hopes are that the ETS is going to increase further, providing part of the financial solution. But I think we need to work as CCS community to try and decrease cost. As for the material that's needed to construct all this infrastructure, of course, today this has to be done with steel mills and cement factories that are not green yet. But that's part of the game, of course. As we build infrastructure, we will be enabling green cement. We will be enabling green steel that can then be used to further expand the infrastructure. Thank you.
Thank you, Philip, for the answer. Indeed, there are challenges that we need to face as the time goes by, and this is important to realize. So I suggest that we have a short break of around 10 minutes, and we will be back at 10:55 for the next presentation by Alberto. So see you in around 10 minutes.
Hi, Miguel.
Hi, Alberto.
Can I
think you
try
joined.
to share my screen just to not to have
Of
surprises?
course. Please go ahead, and we will see.
Can you see the presentation?
I can see the presentation. However, okay, it seems to be loading because the two sides of the slide are cut for some reason.
Okay.
So it doesn't show. It doesn't show the whole score. Let's say.
Is it cut?
Yeah, unfortunately, it is cut. Yes. So if you prefer for us to share it, and
Yes, of course. I'm sending by email.
sounds good. Yes.
To Miguel. Type PDF, it's fine. Good. Okay, just sent.
Thank you.
Is it arrived?
Yes.
Good.
It arrives. Very fast technology these days. So I will share my screen.
Perfect.
Perfect. Well, welcome back, everyone. Now I am pleased to introduce Alberto Giuliano Albo from INRiM, who is going to talk to us about some speed of sound measurements and how these can be exploited for monitoring CCUS processes. Welcome, Alberto.
Oh, thank you, Miguel. Well, this talk is about the exploitation of speed of sound measurements for monitoring CCUS processes. And I tried to select the topics of this talk on the basis of the questionnaire replies that has been recorded. And so I will show you something that we are doing in our laboratories, something that is done in other laboratories. And I wanted to underline I want to report some links that you can visit to get an insight of some of the topics that you are more interested in. But a few words before. Next slide, please. So just a few words before approaching all the topics that I selected. And just a few words on the ultrasonic propagation and principles of this phenomenon. Yeah, well, acoustic waves are a phenomenon of transportation of mechanical energy through an elastic medium. And this medium can be solid, liquid, gas, supercritical, plasma, and and other states of the matter. The idea that is the principle that is behind the measurements made using acoustic waves is that the system is is in a thermodynamic equilibrium, but this introduced mechanical energy from the external of the system perturbs the equilibrium of the system. Well, after that, the system tries to get back to in its equilibrium conditions, and measuring some parameters of describing how the system is returning to its equilibrium can provide information on the state and the characteristics of the matter in which the wave is propagating. Since the speed of sound, for example, is one of the parameters that we can measure after perturbing a system, so the speed at which this energy is transferred, is a thermodynamic quantity, and this has been proved to be of importance when equation of state, thermodynamic equation of state of a liquid are implemented, because it is a property that is linked to thermal but also to caloric properties of the fluid. And today, more accurate equation of state make use of speed of sound measurements to as a value for the validation, but also for the implementation of the model, of the thermodynamic model. Well, ultrasonics are widely used in industry. You know, I'm of course better than me. And as a non-invasive measurements, for example, in non-destructive testing, for example, to examine welding, to analyze solids and other situations, of course. And it's also used to create a pseudo images of the sublayer, that the substrate of a material, solid material. For example, I reported here 2 pictures that are of interest. That was curious because there are 2 operators working almost at the same way, but one is on the knee of a person, and the other one is on the pipeline, on the pipeline. And yes, the idea is that if you work in a medical center, you can't you may not use the glove, but if you are working on a pipeline, it's better to use medical gloves. Next slide, please. So one of the topics that has been lifted in the questionnaire was the CO2 phase identification. Well, in this sense, ultrasonic measurements can contribute to determination of the phase of the system, because there are 2 possible approaches. The first one is when the composition is known, and and a reliable equation of state is viable. In that case, just measuring temperature and pressure usually is enough, knowing the composition, to establish the state of the system. However, there are conditions where the composition is not very well, and we need to know if the system has a significant gas phase or liquid phase inside. To this end, there are research work on the possibility to use 2 sources of ultrasound, one at low frequency in the order of kilohertz, and the other one in high range. This means in megahertz range. The idea is that usually high frequency waves are absorbed by the fluids in gas phase, and so we can evaluate the amount of the gas into the liquid by measuring the ratio of the amplitude of the signals that we have received at the 2 different frequencies. This means that we measure the variation of the amplitude for the high frequency and the low frequency transducer to evaluate the amount of gas that is present in the mixture. Another way to that can be exploited is to evaluate the noise of the high frequency signal when we have a liquid fluid that with bubbles, for example, because the signal traveling into the high frequency signal traveling into the fluid that is in equilibrium with the gas determine as a diffusion of the wave, of the acoustic wave. And so this is something that can be exploited to evaluate the presence of bubble in the liquid. In supercritical fluids, usually it is used both high frequency or low frequency transducers. Mainly, usually it's better to use low frequency transducers because the speed of sound is not very high, and so there are field effects on the measurement of the speed of sound. This plot is for CO2. It is taken from RefProp and represents the speed of sound as a function of the density. And most of the application that you will see in the next slide are based on the description of these plots, where we have the low at low frequency density, we have the speed of the gas phase, and in the high density range we have the liquid phase that is almost linear. I reported 2 references on the CO2 phase identification to if you want to get into deep on this topic. Well, we have also applications on, of course, in flow meters, you know, and there are manufacturers of ultrasonic flow meter in this audience. So I want to focus on calibration of flow meters, not in the principal work. And to this scope, we develop a primary sensor. That means that it measures the speed of sound directly from measurement of length and time, and it is the cell that is represented in gray and red on the small box on the left. When developed this project, when we developed this device, it was for LNG. And we proved that it's possible to liquefy the methane and use this cell to measure the speed of sound of the methane, of the liquid methane. After that, we understood that this cell can be used to calibrate the ultrasonic flow meter basing on the principle that ultrasonic flow meters are able to measure the speed of sound of the fluid when it was at rest, even if there is a flow. And this is the thermodynamic properties that we need, and that we can compare with a reference value obtained by a primary standard for the speed of sound. At the time, we believed that it was one of the possibilities was to have to prepare the ultrasonic flow meter with the possibility to mount this cell when we want to perform the test. But of course, it's something that is invasive because you need bulbs, you need other devices. And because of this, we are starting to develop a clamp-on system that is something that is different from commercial and viable clamp-on, because we want to calibrate this clamp-on using the cell inside the spool, calibrate the speed of sound using the clamp-on, and use the clamp-on system not for measuring flows, but just for measuring speed of sound. And it's something that is work that is going on. Here is a reference if you are interested in. Next slide, please. Well, good. Well, we have seen that there is a link, a strength link between speed of sound and equation of state, but there is a link also from speed of sound and acoustic measurements with the devices that are used to monitor the quality, in this case, or the flow of the gas. And to this end, there is a good interest in develop and to create Internet of Things devices that are able to be set on real plant and adapt them easily to the particular condition of the plant, and so that they are able to collect information, exchange the measurements that they are doing in different places and in different parts or with different techniques in the same plant. For example, Internet of Things applications are already testing in flow meter, in flow metering, in leakage detection, in tanks and reservoir monitoring. The Internet of Things has also the possibility offer also the possibility to integrate well-established measurements, but also the new technologies, because at the beginning, when new technology will be adopted, they should be demonstrated the capabilities before being adopted in a large scale. Well, on the other side, we have the question of state that are used that can be set into these microprocessors equipped with the IoT technologies, and they are used, of course, to convert volume to mass flow, and used to design chemical measurements. I don't want to get into deep on this topic because we have Roland that in the afternoon, I think that we provide much better information than those that can I provide. Just a recommendation, because in our experience, we used many different equation of states, and we want to support to confirm that GERG 2008 has passed all the tests that we had in laboratory. Of course, it's a standard, but even if the reliability of that equation is sometimes still to be checked, every time we check this model in really hard condition, this equation revealed to be robust also in that case. So whenever you need an equation to perform tests, to perform design or something, I can suggest to start using GERG 2008. That is also a standard, so you can use it to calibrate your instruments. Of course, GERG has 21 components in its structure, and that does not include, for example, amines. So, of course, also GERG need to be improved to meet the needs of CO2 in the CO2 field. Next slide, please. Well, the other topics that has been proposed is the impurities, and to this end, ultrasound approach is not based on the speed of sound, but on another phenomenon, that is the absorption of the CO2, that the CO2 molecules show absorbing acoustic energy and then releasing it after some time. That is the relaxation time of the CO2. There are some interesting works on these topics. This technique is called quantitative acoustic relaxation spectroscopy, and as the name said, it's based on analysis of frequency spanning from kilohertz to megahertz of the absorption of the acoustic wave of the system. Usually there are just two frequencies are used, and small variation of these two frequencies are acted to create plots of the response of the system at different frequencies to determine the relaxation time. At the moment, this technique showed accuracy in the uncertainty in the order of 1%, so it's quite large. Anyway, it has some advantages because it's really cheap, and it has a very fast response with respect to other techniques that needs long time, to minutes to get the composition of the system. Some of the impurities that are investigated using also this technique are those reported in this list that is taken from the report of SINTEF that is reported here in the references. And this list does not include amines, and that's why in this project for MetCCUS, the group of the work package dealing with thermophysical properties are working to provide the necessary experimental measurements to improve the accuracy on the models, of course. Next slide, please. Well, this scheme is something that most of you know. That is, it's really similar to a flow meter, but it's something that has been modified in the first reference that I reported here. And it is a system that is a combined. It is a combined system that measures speed of sound and the electric constant. The sensor of the electric constant is on the right, together with the thermometer. There is the temperature on the top right, and there is the capacitive sensor in just below. This is interesting because it allows to combine different quantities collected at the same place and use them to, for example, the scope of this system was to determine the density of the fluid and the water content of the fluid, because this was was implemented to characterize fuels after produced after methanation of the CO2 or by e-fuels. It's interesting because this system is something that we already know very well, because this system is nothing else than a flow meter, ultrasonic flow meter that has used already done measurement to provide further information. And this is a proof that ultrasonic approach do not provide only flow meter information, but can be exploited also to provide much more information that at the moment are not collected. Good. Next slide, please. Well, again, another point that has been, another topic that has been pointed out was the CO2 storage in the site monitor. And in this case, I would show an application that is reporting in references, of course, and that uses subsonic wave. We have talk on most of the part of the topic on the ultrasonic waves. In this case, we are speaking about subsonic waves. In this approach, there is a generator of subsonic waves between 5 and 15 hertz that is set on the surface of the ground, and a network of receiver is set on the ground at different position, at different and known position. Well, the generator generates the acoustic wave that propagates in the medium below it. That could be the sea or the ground, and it is reflected on the substrate of the ground. This allows to create maps of the rocks that are set, and the bubble or the liquid bubble of CO2 that is set below the generator, and monitoring the speed of sound in the measured in the rocks is possible to associate the variation of the speed of sound to the presence of the CO2 that is leaked by the reservoir. There are some examples. For example, in the picture on the right, there is the possibility to evidence a sort of a column formation of CO2 that is getting out from the reservoir in the picture below on the left. Okay, next slide, please. And the end. Well, for the conclusions. Well, I just wanted to point out some possible application of ultrasonic waves in different fields of the processing of CO2, and I proposed some references of new technologies, and we discussed a little bit on established technologies, and I hope to have been able to evidence that this field is something that can be really improved in next year. This is not very exploited at the moment. There are large possibilities to adopt ultrasonic techniques in the field of CO2 processing. Of course, this activity needs the direction of the industries, because it's difficult in laboratories to make a priority of the activity that should be developed in the near future, because sometimes it's in research we can see something that is really interesting and we want to get into deep on this topic, but then sometimes we focus too much on this, but and leaving away something that can have a larger impact with respect to that we are working on. So final recommendation: keep in touch and stay tuned with the MetCCUS project. And for any question, here we are, and we would be happy to reply and to your questions and to have other opportunities to interact with you. Thanks very much for your attention.
Thank you, Alberto, for the presentation. I see that there are a few questions in the chat, so maybe we can address one or two of them. For example, the latest one from Zoe is related to the previous slide on CO2 storage monitoring.
Okay.
Can you see the question?
Yes, I'm reading.
If it's possible for gases.
Okay, the reservoir can contain both gases or liquid CO2. It's not a problem because these measurements are based on the measurement of the acoustic impedance, and the acoustic impedance of rocks is order of magnitude different from that of liquid or that one of gas. So it's a problem that is well established and well exploited. The models are well exploited by companies that are looking for natural gases or other source of energy like oil, mainly oil and gas, of course. I hope
Thanks.
I have given the reply.
Thank you, Alberto. And maybe just one more question from Stefan, the one before about impurities regarding the error.
Yes, at the moment, okay, it's something that is at the beginning. So at the moment, yes, the uncertainty is the order of 1% or a little bit better. It depends on the impurities. At the moment, is something that is there. It's an interesting work, and it is promising, and there are large possibility to improve this technique. For some examples reported in the paper that I put in references, claim uncertainty much better than 1%, but to stay in in a safe condition, because at the moment it's something that is not well established, I put this as an indicator of the order of magnitude at the moment of this.
Thanks, Alberto. And just the last one from Rod regarding the ultrasonic subsurface approach. Is it applicable for offshore storage sites, or has it been demonstrated?
Sorry. Okay, the last question of the second. Okay, Alberto, is the ultrasonic subsurface approach feasible demonstrated for offshore storage sites? Okay, it's absolutely feasible. I don't know if it is already demonstrated, but usually in that case, waves are generated by systems that are floating on platforms or on ship. It's a technique that is well established in the research of oil and gas under the sea. This I reported in references just an application made in Japan. This is in a real implant plant in Japan, developed in 2013, if I really remember, but I may be wrong. And but I think that it's quite simple to find some other application in for undersea.
Thanks, Alberto, for your responses and also for the very interesting presentation.
Thank you.
It was very timely, so I suggest that we move on, and I will share once again my screen. Just 1 second, please. And this time, I am pleased to introduce Salvatore Pitti from Emerson. Also, once again, thank you as part of the members of the advisory board. We appreciate the time that you have taken to be here with us and talk to us. So I will
thank you for giving me the floor. No break at the moment. I will take over the screen and let's see how that is going to work.
Please.
Can you hear me?
Yes, we can hear you.
Great.
And
you can see also my screen at the moment. Huh? Perfect.
Yes.
I put this here. So thank you for the time and for the capability to give a presentation on this floor. Let me first introduce myself. My name is Salvatore Pitti. I am working already 25 years, a little bit more than 25 years for Emerson. And over those 25 years, I've been often involved with custody transfer applications, approvals of our meters in all scenarios. So not only liquid applications, also gas applications. And in this custody transfer world, in the last years, we have also even created a metrology department under the lead of my manager, Yasser Al-Gamri, in which a group is completely dedicated on approvals all over the world for our meters, so that we are all aligned basically worldwide. So now I step over to the subject.
I'm sorry, Salvatore. Sorry to interrupt you, but apparently there is a problem with the screen sharing. Okay, now it seems to work because it was black in the screen of some people.
I'm sorry for that.
But now it's working. So please go
That's
ahead.
great. At least you can see it. But hopefully everybody could hear me. That's the most important to start with. So I want to introduce the subject which I want to describe in the coming 25 minutes. I would like to concentrate on measurements, Coriolis measurements in the CO2 world. I will show you the capabilities which we have and the open standing opportunities. I need to go to the next screen. Okay. And I set up an agenda concentrating very shortly on the scope of this presentation. Then we will have a chapter focusing on what is the stage of approvals at this moment and how are we cooperating in getting those approvals, how are we bonded to different advisory boards or JIPs which are in place. A chapter which maybe is also for everybody interesting. What can we demonstrate? What have we already proven on it? In what type of applications we need to think within the CCUS? A lot of things are slightly a repeat, but I want to prove also what is possible. And then we will have also a chapter in respect to what means calibration of a meter, what means transferability of a meter out of the factory into the field, and we will also prove you some evidence for what is already tested in the field. So let's concentrate very shortly on the scope. There's a lot of history on regulations, and there's a lot known in the oil and gas industry. Oil and gas industry is more than 40, maybe 50, maybe 60 years already in its place. So all over these years, a lot of regulations have been settled. Regulations not only locally, regionally, up to even a level of harmonization. Think about MID, OEML. So a lot of knowledge is in the world in respect to oil and gas. With the renewables like CO2, but I put also here on the agenda H2, which is also very, at this moment, very attractive, and we are following both. these regulations can be not fully copied. The knowledge can be copied, but the regulations they need some slight adaptation. Basically, needs to cope for what is needed in the field. And we have not 40, 50, 60 years again. No, this should happen as soon as possible. This should happen in a short time. So we should be aware that we are awake on what is happening and that we are not going to make mistakes on what is happening. And so this goal that we are all in this community are responsible for what is happening. So we should be very close to each other from all levels, from customer up to entities. So I will give some more inputs on this part. So what our capabilities are, also in respect to the regulations, where do we stand, and more important at the end is also what challenges do we have? What is the next stage to reach? So let's concentrate first on approvals. Approvals are worldwide settled. We have different type of approvals all over the world. We all know API, we all know MID, the regulations which are within Europe, as well we know OEML. And what is the stage at this moment for carbon capture, CO2, in those regulations, in those standards and legislations? Now, shortly, let me put the pointer on. Yeah, this one. Yeah, you can see that CO2 is captured in several standards, but not covering the full aspect which we need. And therefore, you will see API, MID, the H2, sorry, the CO2 is covered, but up to a certain coverage. OEML is even luckily further with it. There's a bigger coverage for us also there, and we concentrate on OEML. We have the R137, which is meant for gas and supercritical conditions, and we have the liquid stage, the R117, which is covering basically the liquid. Also here we have done already out of ourselves also big steps. MID is also in place for that. So then settling the relevant regulations and recommendations for both H2 as CO2, and we see that there are not so much regulations, first of all, for the H2. For the CO2, we see more regulations, but what is also particular is the maximum permissible errors in those regulations are not aligned. You see sometimes 1.5, you see sometimes 2.5, and that can be all caused because in one regulation we have only to deal with approval on the meter itself, and in another regulation we have to deal with approval for complete system. That could be the cause for the differences, but alignment would be appreciated for all parties, I would say, at that stage. And so therefore we as a manufacturer would like to be close to what's happening with those approvals, with those regulations. And here's a sheet where we show worldwide that we are participating at those communities in all extent at the end. In the States, different. In Europe also. In Europe is very well known a DNV test where different manufacturers are also involved in testing the meters, calibrating the meters on CO2. At DNV, they have that laboratory available. Or we are participating in this particular consortium, the MetCCUS, of course. So we like to be close to what is happening on the world. And if we need to assess or discuss, then we are closer and just in time to say our wordings, basically. So now let's concentrate on applications and the measurements which are done in the CCUS world, basically. And in general, the the CCUS is looking, and that was already also explained in previous presentations. TNO did a great job on that, of course, and everybody. The applications are very varying, and we see from carbon capture up to carbon storage, a lot of applications in between. So we need also to concentrate on transportation and distribution, or we need to concentrate on ship loading and offloading. And there are so much different applications available that also the process conditions are not the same. And therefore I put the CO2 graph, which is for everybody already known there, but applications vary in process conditions. Either we are working in a gas stage, low pressure, high temperature, or we are working in a field in a dense phase, as it was already mentioned several times, in a liquid phase, dense phase. There we have to deal with high pressure, or even up to a supercritical condition, when we are working above the critical point, basically. And the challenges which we have as a Coriolis manufacturer is that we need to deal with the different stages, and we know that at the different stages, different effects could be part of the game. In a gas phase, for instance, predominantly a velocity of sound effect is present. And we know what the effect is, so we are able to compensate for that. That's great. I will show you in the next sheet what the effects could be and what they are. In the dense phase, the challenge is that we are operating at higher pressure. We see up to 150 and sometimes even higher pressures which are used in the field. When we are operating at higher pressure and we have to deal with a bigger meter which has some pressure effect, we need to compensate for that. We know what the effects are. These effects are not random, but these are always in one direction. So we are able perfectly to correct for it. So in a short wordings, for all these type of variations, a Coriolis meter, our micromotion meter, can be easily used. It will fit in the applications depending on the flow rate which are in place to be used. And then you have a direct mass measurement out of your meter. Then again, a short repeat on from captured to storage, that different process conditions are valid. In the first stage, it can be more a gas phase, was also mentioned in the previous presentations. In the transportation mode, it can be both gas, but sometimes also liquid conditions could be selected. It's depending on the future which we will have, and also in the storage point, our meters can be utilized up to, again, a liquid phase. So let's now concentrate on what could happen in a meter under a gaseous meter. There's effects which are known. We are open for that because these are visible. These are already demonstrated by also universities around. Mr. Kutten and Mr. Hemp have been already made articles on the velocity of sound effect in 2006. So this is a phenomena which is not known from yesterday, but already a longer time. And this velocity of sound effect is an effect caused by the compressibility of the gas, basically. And that is valid for all gases. It's not valid only for the CO2, on which our concentration is at the moment. But if you have an older gas, you have also to deal with the same effect. But the effect is not always the same. It's not has not always the same magnitude. And what is giving the magnitude of that effect? That effect that is analyzed again by the Kutten. The effect is notified here in a formula. This is an estimated formula for what the effect is delivering, and there we see parameters like frequency of the meter. If you have to deal with a meter with a high frequency, then you will for sure have a bigger effect due to this velocity of sound effect, due to this effect. Another parameter which is important to take into account is, do we have to deal with a big diameter throughput in our meter, or do we or do we have to deal with a small meter? When we have to when we are cooperating or using a small meter, the effect is very small or even negligible. So that's also to take into consideration. So the effect, you will not see that effect on all meter sizes at the end. And also a very important point, which is also meant, the effect is depending on the fluid, on the product which is used, because each product has its own velocity of sound value. Yeah, and so that is what we concentrate basically on. And on the next sheet, I show you that on the graph I've put several products, and for each product another velocity, speed of sound, velocity of sound effect is known. For instance, for helium, the speed of sound is around 800. So the effects which we will see are much less as I would have to use, for instance, CO2, because CO2 has a very low velocity of sound, but that is causing a bigger velocity of sound effect at the end, if we follow the formula basically. And the values, you can see the value is giving the effect is giving a positive error, reproducing depending on the meter size, of course, and that is the reason why we can correct for it. And that correction we have already implemented in our electronics. So there's already a solution in place for this kind of activities. And I will show you in the coming graphs more on it, because we have done also tests at the laboratory all over the world. I mentioned first Groningen. In Groningen, they have the DNB lab in Groningen. They can do, of course, CO2, but also in Canada, there's a CO2 lab. Now, we have been there to retrieve our OEML certificate basically on it, and we have tested there with two different sizes of meter, a small meter and a bigger meter. On the screen you see the bigger meter, but let's first concentrate on the smaller meter, which is a 3-inch meter, and the errors are all within that maximum permissible error, which is valid out of OEML of 1%. So it's very clean what we see here. If we then concentrate on the bigger meter, the CMF 400, where with CO2 also the effect is corrected for, so the velocity of sound effect is also corrected for, then you see also that the errors are very well within the maximum permissible errors. And before I continue, I will show you also again in the next sheet, all these calibrations at these labs are done with the flow curve factor, which was determined in the factory. And how do we determine the flow curve factor in the factory? We use a water calibration. With the water calibration, we have done with the parameters determined on the water calibration, we have done this calibration at the CO2 in the field. Just to point out at this point. They were also done, and we heard also in the previous presentations, effects of impurities. What's the effect of impurity during the test? Also in the last years, several years already, we have concentrated on that. We have done these kind of tests on CO2 again, with impurity in the line, and the majority was nitrogen, which was used as impurity. And the errors which we obtained were all within 0.25%. So that's one fantastic result out of this. Of course, we need to notify In addition, very shortly, if you have to deal with a meter where the frequency is would be higher, then of course the effects of the impurities will be also bigger and more visible. But for our meter, that's not the case. The frequency is reasonably low for the meter. Here on another sheet, concentrating on the impurities which we have tested with that kind of meter. And here we had the impurity at this test was the test was done with natural gas, and then the impurity was the CO2. So we had up to 20% CO2 in a natural gas mixture working at 16 and 32 bars. And you see all the arrows on the screen, and these are very well within the 0.35%. And if we would look then to the overall classification, which is most of the time is 1%, yeah, I can only say it's very well within that specifications. Now the proof of that transferability, because that will help us forward for what do we need to do in the future. What can we do? We need to test up to a certain level. We need also laboratories to test. Not all laboratories can give us all process conditions. That's unfortunately also the case, because the world is just now starting basically with CO2. And I have the same challenge basically also for hydrogen. I need still to mention that in comparison to that, because for hydrogen also there is not so much references around at this stage. But the world is evolving, and therefore we are very close to these evolvements. Oh, I need to go to the next sheet. So this is a statement which we see here on the screen from the notified body NMI, where the water calibration is transferable to another gas. And this statement is already several years old. Within the MID, we needed to get also that statement under control. At that moment, a lot of tests were done for natural gas, but that was the base, and the story for CO2 is not different. It's only another product, and as long we know what the effects are and how to correct for the effects, the story is exactly the same. So this is only stating we have settled the flow-cal factor on water, and we maintain that flow-cal factor also in the field for the gases has been used. That's our step 2 basically. And then we need, of course, to meet the MPEs which are valid in the statements. And for the gas, that is 1% basically. And we have that transferability in place, because if we meet our water call to be within 0.3%, and that's always the case, otherwise we will not ship out any meter, then that transferability is automatically also in place. And in the field we have all additional activities to undertake in respect to zero the meter and all these kind of things. I will not discuss this in this session. I hope the next time I would get more time to explain a little bit more. Of course, I'm already pointing to the next time, but let's first finish this one. Here's a proof again. First, I start with a natural gas calibration. This is the small meter. We did the first water call. This in the bottom part of the sheet. You see the water call. And again, with that flow-cal factor, which is determined on the water call, we have been at the gas lab. Can be Pixar. This was natural gas. I believe this was at Pixar. We maintained that same flow-cal factor and did the test at the different mass flow rates, basically. And you see here the curve very well, very well within the maximum per mass errors for the gas. This is natural gas. Of course, we are all interested in CO2. And here's again a curve showing for the water call, which was determined first in the lower end. You see the same flow-cal factor is used in the field with CO2, and the arrows are very well within that maximum per mass. Oh no, sorry, I do not know why, but somebody unmuted. one way or the other. I continue. So that is also proven that is in place, basically. Next sheet. Yeah, so we are almost at the end of the session. So again, for CO2, we have done several tests. We have not only done the test with pure CO2, we have also checked what happens with impurities. We have done that kind of test all over the world at different labs, of course. But in Canada, we could test with 90% CO2, and the rest was, for instance, N2 in the line. Sorry. And that is in respect to CO2. I want only to notify you, as I am also very close to H2, and which is not directly linked, but still linked in the way of today, that also with H2, we show the water transferability on it. And the graph is basically showing you the outcome for test, even up to 700 bars on H2. And even slightly higher, I believe we were. Okay, next sheet. That is in summary. I want to close in a short summary, so that we have shown you in this short presentation the fit for purpose. Basically, the meters are able to calibrate to be used on CO2 applications, not only on gas, not only in dense, not only in supercritical, but you can use them all over. Of course, one condition at a time. That's one thing I need to add on all this. Traceability, that is also a point which I touched. Laboratories give us traceability for CO2, H2 I use also. These are coming up. But I would like to see sometimes also that they are aligned with each other. And those challenges are sometimes also at the lab themselves. But we have proven our meter meets the expectations with the different extremes. Standards, that's the base for knowing how to sell, to knowing what are the maximum purpose of errors. These are coming up. There are some are set, and we see also that OML is very well has a big coverage already on CO2 and H2 itself. But I'm for sure in the coming years the coverage will be even better because of demand, because of request, because of regulations. So far, this very short presentation, and if there are questions, I'm here.
Thank you, Salvatore. Actually, there are a few questions in the chat.
Okay. Okay, I need to check that.
Please have a look. And for example, there is one related to your slide number 10 or 11. Someone is asking what were the axes, because in the chart that was shown in that slide, it doesn't say the x-axis or the y-axis corresponds to.
Sheet 10. Let's go first to that. We need to. I do not know how much time I have, but I take my time, otherwise you close me.
Yeah, you can answer one or two questions because
sheet 10
maybe
is.
I think
Sheet 10 is here. Is it this sheet?
That one, yes, correct.
That one. Oh, so on the axis, you see here the speed of sound of the meters. The speed of sound is meters per second. Okay. It can be also in other units. You are right. I'm sorry for that. I did not put it on the sheet, but it's the speed of sound of the product, which is notified as with the units meters per second. And on the y-axis, you see the effect, the effect, which is composed, which is a percentage value. So you will see for a CO2 and a bigger meter, you could have effects between 1%, 1.2%. But as long as everything is repeatable, a correction can be made, and that is done. That is the first question. And now I need to go. I hope I answered that question.
Okay, thanks. And maybe just this one, we have just 1 minute left before the next speaker, about the current limit of size in Coriolis meters, now that we have like large scale
Yeah,
pumps.
we have the current limit, the biggest meter is an HC4 for us, and that's about 12 to 14 inch meter size. We should look to that. And of course, this is a little bit the maximum size which we have in place at this stage. And of course, depending on the applications, we are further looking to how can we solve it. Sometimes 2 meters in parallel are easily used in these kind of applications. So it's really depending on the process conditions to analyze what is the best fitting meter. And in most of the times, mass is very crucial. So our meters are also giving directly mass as output. We should not, I do not want to forget that is also a crucial part in all this.
Perfect.
If there's more questions, again, I can an email can also be sent to me, and I can also on a later stage give answers on these questions. It's no problem for me. Yeah.
Thank you, Salvatore. Sounds good. We will contact you afterwards for more questions if needed. And yeah, if you want to have a look at the chat to write there directly. Thanks once again for the presentation.
Thank you. Have a great day. Bye-bye.
Goodbye. Now moving on to the next speaker in the program, I am happy to introduce Aurélie Moll from SIG, who is also among the stakeholders that are in the advisory board of MetCCUS, and she's going to talk to us about the CO2 measurement needs along the CCUS value chain. Thanks for accepting the invitation and welcome.
Thank you very much to have inviting me. I will share my screen.
Sounds good.
Moment. I'm trying.
It works
okay,
now.
Can you see?
Yes.
Can you still see the screen?
Not anymore. No, it disappeared.
I have some problems. I try again. So. Next try, and now?
Now it works.
Okay, perfect. Thank you very much. So then today I will give you an overview about measurement, and especially for CO2 measurement along the CCUS value chain. I will first give a short introduction, some words about the topic of decarbonization and the role of CCUS, and then we will go more in detail about sensor solution for the CCUS value chain, and especially for the CO2 measurement. So first, I would like to give some words about my company, SIG. SIG is a German-based company with more than 75 years of experience in sensor solution for industrial applications. We have nearly 12,000 employees worldwide, sales amount of 2.2 billion euros, numbers from 2022. And we also invest more than 240 million euros in research and development, so making SIG one of the most innovative company on the sensor market. Here we see different type of industries where CO2 is emitted, and all those industries will need CCUS to reach their decarbonization target. With our product portfolio, we can solve nearly every industrial application, but especially for the topic of today, the part with gas analyzer and flow measurement are very important for carbon capture. So regarding the decarbonization trend and the CCUS, now all international organizations agree about the fact that the net zero emissions will not be achievable without the use of CCUS, additionally to other measures like increase the energy efficiency, move to clean energy, and so on. That's the case for the IPCC, for example, or from the International Energy Agency. What is important is the capacity that is required for the CCUS. You can see it on the right-hand side on the graph, how much gigaton CO2 have to be captured per year until 2050. That's a huge amount, and that's also a huge growth in the next decades. So a big topic for all of us within the industry. And we see also a big push coming from policies and regulations, especially in Europe, with the target reduction for greenhouse gas emissions of 55% until 2030. And we can say we are nearly in 2024, so the time is going very fast. The price of CO2 is also a big driver, and we saw also the last years an acceleration or an increase of the price of CO2. And also there are a lot of funding, public and private funding for CO2. Here, to conclude on the market part, we see also an acceleration in the development of CCUS project in the last 4 years, I would say. So with main focus in North America and especially Europe. That's why we are here always also. What's important also for me to remark is that the projects that are in the pipeline today or last year we're only accounting for nearly 240 million tons per year CO2. And when we remember the numbers from the International Agency, we are speaking about gigaton CO2 per year. So we need a lot of plants, infrastructure to develop this CCUS market. But now we will see what kind of sensors are required to optimize the CCUS value chain or to control the CCUS value chain. First, we are speaking about a value chain because it is not only about capture or about storage, it is about the complete process. So the capture part at the industrial emitters, or for gas production, for example, hydrogen or ammonia. There is also a new topic, which is the direct air capture, where the CO2 is directly captured from the air. So a lot of different applications. We have the transport part, but it is not only a pipeline, it can be also trucks or ship. And then the storage, the utilization. And everywhere for all the steps, we need to have a precise and continuous measurement of the CO2. We have seen the flow part before, but the gas analysis, the quality is also very important. Also, because we are speaking more and more about hubs and clusters for CCUS, the measurement part is they're very important because those companies are going together to collect their CO2 from the emissions. They are using common infrastructure like pipeline, for example. They are investing in common infrastructure. So all those things are helping to optimize the cost for CCUS projects. But then you have several different interfaces and you need this precise and continuous CO2 measurement, especially when it comes to reporting or accounting, for example, to claim for tax credit or for CO2 removal certificate. On this graph, you see an overview about or an example of a CCUS value chain with different industry, different pipelines, and where you where the plus signs are in orange or in blue are, for example, the needs for analyzer or for flow meters or both. Why do we need those analyzers? The first thing is to control the efficiency of the capture processes, so mainly at the emitter sites, and mainly with CO2 concentration before and after the scrubber. You also need to control the quality of the gas. For example, what kind of impurities are in the gas. This is also very important for the further step, like the pipeline transport. And the last important things is, of course, the reporting of the CO2 that has been captured. For this, at SIC, we have different type of analyzers or flow meters. And depending on the applications, if we are at the capture size, also which kind of industry, so which kind of component has to be measured, then we are using different type of analyzer. For CO2, the most easiest one is to use a single component analyzer to measure the CO2 concentration. It can be up to 100% CO2. If you need more than CO2, for example, impurity measurement, you can use multi-component analyzer that can measure, yes, from 1 to 3 components up to 12 components, for example. There is for me also a new topic. I think this is not part of this project with Euromet, but we saw the last weeks or the last months also some requests for dust analyzer, mainly regarding the capture part to protect the scrubbers from the dust. So this can be also interesting. And the flow part, of course, we have heard about Coriolis technology before. We are working with ultrasonic flow meter that are well known in the natural gas physical metering and can be applied also with some adaptation for CO2 in gas and supercritical phase. Of course, we are also providing turnkey system with complete integrating system as well as digital solution. And this is also very important for the CCUS valuation, especially when it comes to reporting. Another topic that is not directly about CCUS, but linked to CCUS is the greenhouse gas monitoring and reporting part. The CO2 is a big part of this. Not only, there are also other components. And when you take all the steps, the measurement, so precise and continuous measurement of the components, the flow of the exhaust gas, you need some validation and verification steps, for example, with the TUV, the digitalization of the data with reporting calculations. Then each emitter can exactly measure, calculate, and report its CO2 emissions. And on a similar way, it is also possible to have the same reporting for the CO2 that has been captured. Now, I would like to give some example of application where we measure CO2 concentration. The first one is probably well known. That's the LELAC projects for the cement industry. The first one was in Belgium, and with this process, the unavoidable CO2 that is emitted via heating of the limestone is directly separated from the process, so without any scrubber. For these projects or pilot projects, we delivered some analyzer. For example, we had 2 analyzers for the combustion control, which is a more standard application for us with CO and O2 measurement. And on the other side, after the separation, an in situ analyzer to measure the CO2 concentration that were more than 80% at this stage. Then we can take the example of a capture with solvent-based scrubber, for example, an amine scrubber. Such carbon capture technology can be retrofitted to each industrial plant with flue gas emissions, and it is installed normally after the standard flue gas treatment step. So there, it's important to be able to control the different CO2 concentration to have an exact view on the efficiency of the capture. So you can measure at the inlet of the scrubber on the flue gas side, the so-called raw gas, CO2, but not only. CO2 is important, but you need sometimes to have other parameters like SO2 or SO3 to protect the scrubber. On the other side, you have the CO2 lean gas that is going back to the stack. There, it's also interesting to have the CO2 concentration, mainly less than 3% in volume. For your emission reporting, for example, for the greenhouse gas emission. At this stage as well, sometimes other components can be required to control what is exhausting from the scrubber. And a third measurement is also necessary. That's after the desorber, so the CO2 rich gas. There, you can measure the CO2 quantity or concentration that has been captured from your flue gas. Normally, the concentration here are more than 90%. And we have also some example where we delivered extended measuring ranges, 95 to 100% in volume CO2 for this captured CO2 in order to increase also the accuracy on the measuring range. And this measurement will be important for the reporting, accounting between the capture side, the operator of the pipeline, or the storage side. This is an example of measurement task at a pressure swing absorber to capture the CO2 from coal-fired power plants. Here you see there are different steps for the capture. So after each step is also important to control the efficiency, to have a look on the concentration of CO2. So step one, after the capture, you have CO2 between 60 and 70%. So for all this measurement, we have used cold dry extractive analyzer. And you can see on the bottom of the slide, the measuring ranges. So the first one was 60 to 100%. The second one, which is the lean gas that is going outside the absorber, CO2 0 to 5%. And after the second step of the pressure absorber, we are above 90%. So there we had a measuring range 80 to 100%. Or we can also have this extended range 95 to 100, depending on the process. So I come to my summary. So the first thing is, of course, that we all know that CCUS is a key element to limit the global warming and to reach the target with the greenhouse gas emission reduction, especially when it comes to fossil-based energy, or we have seen it with the LELAC project for the reduction of process-related CO2 emissions, for the clean gas production as well. And for all those applications, we need the continuous measuring technology to control, to optimize the CCUS processes, to control the value chain, the transport of the CO2 or the storage. Efficiency is one of the main important part for the captured. The quality of the gas matrix, especially to avoid, for example, corrosion, and flow metering for the quantity of the CO2. But we see a lot of challenges because of the diversity of application. So for the measuring technology, you have so much different tasks, different components, different concentration. It depends on the capture processes. It depends on which industries you are, what kind of transport. Is it a liquid phase? Is it a supercritical phase? And then when we look further with utilization, for example, there are plenty of applications. Then a big challenge for us is also that we still see unclear and different specifications for CO2, for impurity. What are the uncertainty that are required? Which kind of measurement needs to be continuously measured? There are already analyzers on the market to solve a lot of applications, but at the end, the development also of new products will strongly depend on future regulation and policy that will come in the next years for CCUS. And I'm happy to be part of this conference today and projects because I hope that it will bring more clarity also in the next years or in the next months about the task for the analyzer supplier. What do we have to develop further? In which direction we have to work? So I've put some links in the presentation. I think it will be shared later. So if you need more information about the different solutions we provide, you can have a look there. And with this, I'm done. Thank you very much for your attention, and I'm happy about questions. Thank you.
Thank you, Aurélie, for the presentation. It was really interesting to see once again that there are many CO2 measurement needs in the CCUS value chain, but that there are some solutions available. Some of those that you described, for instance, related to flow metering or the gas analysis of the CO2 and the importance of the different stages of the value chain. So for capture, it's important to consider which type of capture technology is used and when it's necessary to perform these measurements, if it's a scrubbing unit, PSA, and all of that. So thanks a lot. For the moment, I don't see questions. Oh, there is one question that appeared. I don't know if you can see the chat, Aurélie.
I will have a look. One moment.
Yeah. Have you got anything for measuring the atmospheric emissions, stacks, diffusive, etc.? That's basically the question, because you talked about sensors.
I talk about sensor in general, but I talk about gas analyzer. So of course, along the CCUS value chain, you have everywhere measurement. You have also continuous monitoring system for the stack emissions, for example. For the diffusive emission, I think you mean, for example, some gases that could slip from pipelines. In this case, we at SIC, we are not present on this kind of applications. But for each stack where you have an exhaust case, then we have different type of analyzer for each application. So regulatory emission monitoring system with certification, for example, TUV or MCERT certification. We have it. For pipeline, I think there are also not really clear regulation for diffuse slip gas measurement from the pipeline today.
Thank you, Aurélie. For the moment, I don't see any more questions. If there are no more questions, I suggest that we go for the lunch break. But before leaving, I want to emphasize on the fact that we have a survey that we would like all the stakeholders to participate, because we need all your inputs in order to make sure that the MetCCUS project is aligned with all your needs and your interests. So we really appreciate if you take around 10 minutes of your time to fill in this survey. It has some questions that will help the project to continue to move in the right direction. And here is the link. You can click on it. Thank you everyone for the attendance, and we will resume at 2 o'clock Central European time.